We're going to look at two different protocols and start with the simplest one, which is the so-called BB84 protocol. This is simply named after the people who came up with this idea, Bennett and Brassard, and the year in which they published this. This is a protocol that sends information bit by bit, or indeed quantum bit by quantum bit, so operates only with individual quantum bits and therefore does not even make use of entanglement. And in here, Alice is going to prepare each of these quantum bits in one of the following four possible states. The computational basis states 0 or 1, which are indeed going to be interpreted as a 0 or 1 of definite information, as well as our even and odd superpositions. And these we will indeed still associate with definite states of information, 0 and 1, however not carried out in measurements in the computational basis here, but in a basis associated to the X operator. So the computational basis, the measurements are related to Z, so these outcomes are related to the Z operator by just doing measurements in this combination here. And we can simply do measurements also with this combination here. So the outcomes would then be 0s and 1 in both cases. These are just the eigenvalues of these observables. And the associated eigenstates are these two here for this kind of measurement there, and these two here for this kind of measurement here. So these correspond to different kinds of experiments that you can carry out on your qubits. For instance, when this is a spin with magnetic fields aligned differently in space, or for photons measuring their polarization into different directions again in space. Next, Alice is simply sending these quantum bits to Bob. So these quantum bits, without any further modification, are now in the possession of Bob. And what Bob is going to do is to carry out measurements randomly selecting whether this is the observable using Z or X. So this observable here or this observable here. And now he will find outcomes of 0s and 1s. But what is important is to realize how these outcomes are related to the states of the quantum bits which Alice sent. And there are principally two different cases. Bob's measurements, utilizing Z or X, might coincide with the basis in which Alice prepared her quantum bits. So Bob's measurement might have involved, for instance, the observable Z on a quantum bit which Alice prepared either in the state 0 or in the state 1. And in some other instances, Bob might have carried out a measurement utilizing the observable X on qubits which were prepared by Alice in these two states here. And in all of these cases, the measurement outcome which Bob obtains coincides to the classical bits which Alice has assigned to these quantum states. So when Alice assigned these classical bits to these quantum states, and Bob carried out these specific measurements here, then his measurement outcomes simply coincide with these classical bits here. And whenever this happens, these bits qualify as a part of a key. However, there are also instances where we have these quantum bits prepared by Alice in one of these states, but the randomly chosen measurements of Bob simply use the other observable, the one which is not associated to the basis used by Alice. And in this case, for each of these quantum bits, Bob will obtain random outcomes 0 and 1. So these outcomes are then completely random and in particular unrelated to the classical bits which Alice assigned to these quantum bits. So Alice does not treat these quantum bits in any different way, but in this case, Bob does not obtain any information about the classical bits which Alice has assigned to them. So whenever we have this situation, the bits which Alice and Bob have are identical, so this is very usable for a key, but this does not apply to this situation here. So all that Alice and Bob need to do is to interchange some information. Alice will disclose which basis she used. So for each quantum bit, she specifies whether this was the basis associated to Z or X. So this lets us know that the quantum bit was sent as either 0 or 1, or perhaps as plus or minus. But in both cases, it does not disclose any more than this. In particular, it does not tell you whether the state was specifically the state 0 or the state 1, or whether it was the state plus or the state minus. We only know that it was one of these two states or one of these two states. And similarly, Bob discloses, possibly quite publicly, whether his measurements were carried out using the observable Z or X. And as he carried out these measurements randomly, this will not necessarily coincide with the basis chosen by Alice. However, both of them now can simply compare this information and therefore decide whenever this situation occurred or this situation occurred. So Alice and Bob sent each other some strings of X's and Z's. And in the case of Alice, this simply corresponds to the chosen basis. And in the case of Bob, this simply corresponds to the measurements carried out. And whenever these symbols coincide, such in these cases here, then the classical bits which Alice has assigned to her quantum states, perhaps these ones here, simply coincide with Bob's measurement outcomes. And in all the other cases, these bits of Alice's are not related to the bits of Bob, so they might sometimes agree, but they might just as well not agree. So in all of these remaining cases, Alice and Bob simply cannot be sure. And what they therefore should do is simply to discard these instances here. And what remains is simply their shared key. So in this example, the key would just be this sequence of bits here. So this definitely generates a key which is identical for Alice and Bob. And when we look at the mechanism, we also recognize that it is pretty secure. And this has two aspects. And for this, we look at the two stages where communication appeared. Well, at the end, Alice and Bob interchanged symbols X and Z, but these are completely independent of the key that they obtained, because this is based on a different random process, namely the random process which Bob used to decide which measurement to carry out. And Alice, of course, also earlier sent the quantum bits physically to Bob, and so these could be intercepted. But for each of these quantum bits, you might have these two states 0 and 1 with equal probabilities 1/2, or you might have these two states, again with equal probabilities 1/2. And each of these cases separately just give you a reduced density matrix of the same form, namely the form that does not carry any information. And what is really important and clever about this protocol is that at this stage, Alice and Bob have not yet disclosed these symbols X and Z here. So if you were to intercept one of these quantum bits, you would not know which measurement to carry out to obtain the correct information. If you knew in which basis these quantum bits have been prepared, then you could of course carry out the corresponding measurement and obtain the corresponding result. And even if this was sort of a destructive measurement, say on a photon that you have absorbed, you could just generate a new photon in that particular state and just pass it on to Bob. And this would make it impossible for Alice and Bob to detect that somebody has interfered with their process. However, the person who intercepts the signal does not really know which of the bases has to be used. So the only choice for the person who wants to interfere with this quantum key distribution protocol is to do random measurements on these intercepted qubits. So in 50% of the cases, they will indeed guess the correct observable. But in the other 50%, they use the wrong observable. And again, in half of these cases, they got the wrong result. But that's not even the key point, because even if they obtain the right result, they might still pass on the wrong quantum bit to Bob. Now this will happen exactly in 25% of the cases. And what this results in are simply some errors in the key shared between Alice and Bob. Now this sounds a little bit problematic, but it is indeed useful, because by sharing just a very small part of their key, Alice and Bob can now detect whether somebody tried to interfere with their process. And when one now estimates of how much of a key typically has to be sacrificed, then one quickly realizes that this is a very small part indeed in order to obtain a high confidence into the integrity of the key. And this is simply because the person who wants to intercept the signal has to make many independent guesses and needs to be fortunate to guess correctly most of the time so that they cannot be detected. So this is our first quantum key distribution protocol, and what it exploits is really the randomness of quantum measurements, in particular when one deals with incompatible observables such as X and Z. Because in that case, the definite states of information for one observable really look like superpositions from the perspective of the other observable. Next, we turn to our second protocol, and in there we are going to utilize pairs of qubits and indeed entanglement.